if you want to hear the song of the universe, if you have two black holes that are dancing around each other and merging, that might sound something like whoop. Welcome to the Emergence podcast, where we discuss interdisciplinary and collaborative work that connects to U of I physics. A quick disclaimer before we get started: the views expressed in this podcast do not necessarily represent those held by the physics department or the University of Illinois.
I'm Maddie Stover.
And I'm Mari Szynski. We are PhD physics students in the physics department, and today we are joined by Helvi.
Welcome, Helvi.
Thank you.
Helvi Witek is an associate professor of physics at the University of Illinois. Her research interests include gravitation, cosmology, and astrophysics. She was born in East Germany and received her PhD in physics at the University of Lisbon, Portugal. She worked as a research associate in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. From there, she was a research fellow at the University of Nottingham, a Marie Curie Research Fellow at the University of Barcelona, and a Royal Society University Research Fellow at King's College London. Welcome, Helvi.
Thank you so much for the invitation.
Of course. Happy to have you on.
Yeah. So, Helvi, what happy accidents and strategic choices got you to this point in your career? Okay, so there are two ways to answer this question, and maybe you can tell me what you want to hear first. One is to think about what brought me into science in the first place, and then the other one is choices that actually brought me here once I decided to become a physicist.
Yeah. If you could start with how you got interested in science, that'd be perfect.
Okay, good. So I think the first memory that I have goes back to when I was a little kid. And I was an energetic little kid. So I would wake up at 6 a.m, fall asleep at 10 at night, and my poor mom had to somehow get me sleepy. So she would take me on walks outside. And I'm from an area in Germany that is pretty rural, so we could see the night sky. And instead of getting tired, I was just mesmerized by the beauty of the stars in the night sky, and would ask, where do they come from? What are they? And of course, as a little kid, I wouldn't know, but that I think is the first memory for me, becoming interested in what we know as astrophysics now. Later on in my teens, I came across a book called The Brief History of Time by Stephen Hawking, where he describes black holes. And of course, they sound very exotic, but I was again mesmerized and fascinated, so much so that I decided to become a physicist and actually learn more about these objects. That's what brought me into becoming a scientist.
Yeah, that's fantastic. We were talking about this earlier, but myself and others also really got hooked in by A Brief History of Time. It's just a very beautiful narrative of kind of modern physics. And then you also alluded to some strategic choices kind of later on that got you into specifically to the University of Illinois.
Yeah. And I think the first really lucky choice that I made was after my undergraduate studies. So I knew that I wanted to do a PhD in physics. I knew I wanted to go abroad outside Germany, just to have an opportunity to broaden my horizon, live in different cultures. And my family background is a very poor one. I grew up in a single parent household. So for me, the only choice to really travel the world was through my work. So I applied for a PhD mostly in Europe, but outside Germany, and then had several opportunities. And the one in Portugal was the most interesting and the most risky one. So that was to apply the knowledge about black holes that I had from an undergraduate research course, to high energy physics and particle physics. So that was from the get-go, this is really interesting. We don't know whether this is going to work out. Are you willing to try it? And I was like, yes, that sounds exciting. So I went with it, and was really fortunate enough to have a very successful and original work during the PhD, and to work interdisciplinary. So I interacted and worked in astrophysics and gravitation as much as, particle physics and a bit of what we call high energy theory, and made the connections across all these different fields also in terms of collaborators and colleagues. So I think I was very fortunate in that. It was a very lucky choice.
Yeah, that's a very natural networking for the rest of your career as well.
Yes.
Yeah.
And
Awesome.
it was really lucky because I did have an option to go for something that was much safer, but also the funding was clear from the get-go. Whereas Portugal was more exciting, but it actually was unsure whether I would get the fellowship because the results came out much later.
Oh, okay.
And I found myself writing pro and con lists. So I do like writing lists.
Yes.
And I just noticed myself writing and finding more pros for Lisbon and for this more risky project.
Yeah.
And so this is how I knew this is what I really want to do.
Mm-hmm.
And I still do that today. If I have to make a decision, and I write pro and con lists, and I see what I'm going for.
Yes, it's helpful to kind of categorize your thoughts in that way.
Yes.
Yeah. And so some of the pros in that situation were you're just really drawn to the work and the collaborations in that project.
Right. Yeah. And I mean, living-wise, some of the other offers were from the UK, and living-wise, I think would have been fine either way. And I, in fact, worked in the UK later as a postdoctoral researcher. But yeah, so I think it was mostly about the research and the possibilities that might come along with it.
Yeah, and they did pan out.
Yeah.
And did you enjoy living in Portugal?
I did very much. It's still one of my favorite places. Also go back and visit.
Yeah.
In terms of the community and the people that live there.
So a common theme in your work is studying situations where gravity is strongest. For instance, you study black holes, objects with such strong gravitational pull that not even light can escape. What motivates you to study scenarios where gravity is so strong?
Okay. So overall, I think black holes are really fascinating objects where the very fabric of space itself ends, right? So this is really cool. And it's not just an exotic object, we also observe them. Nowadays, we know they're out there. But on much more general grounds, I really like to push to new frontiers in physics, and that means to go to new extremes. And in gravity, I was thinking of an analogy, maybe also for our listeners, and why is this interesting? So if you think about, just going down with your car on Green Street, going from Urbana to Champagne, you don't need Einstein's theory of general relativity to describe that, right? Classical mechanics that you might learn in high school, or I don't know if you've seen this in university, is enough to, say how the car moves down. Now, if you were to go much, much faster, almost at the speed of light, then Newtonian or classical gravity, as we know it, actually breaks down. It cannot describe it very well, and we have to extend our theoretical understanding of the laws of physics. And the next one is Einstein's theory of general relativity that I just mentioned. And that describes well when you move very, very fast, close to the speed of light, if you have very strong gravitating field. So gravity is so strong that your space-time itself is curved and actually gives rise to black holes. Yes, please.
Yeah. So when Dr. Witek is talking about the sort of this bending of space. So kind of a useful analogy to think about gravity is so we're taught that it's like a push and a pull, when we take our interphysics courses. But a more accurate analogy is if you think of a kind of a trampoline surface, and if you are sitting in the middle of the trampoline kind of like warps down towards you. Right. It's not a perfect analogy, but that is kind of the most useful day-to-day thing that you might have experienced. So when she's saying it's so strong or it's like ripping through that fabric, it's because the thing in the middle of the trampoline is so heavy, it's like pulling it really, really far down to the ground.
That's right. Yes. Thanks for that.
Of course.
That is a good analogy to see what do I mean by curvature. Yes. Exactly. And now take your friends and sit down and try to sit together in the same spot. And you see that the trampoline actually goes down further and further until it almost breaks down.
Exactly.
I think this is extremely fascinating, and studying black holes tells us something about when gravity becomes so extreme that space ends. As you said, it would be like the trampoline is really breaking down and breaking up. So one of the things that I'm studying with black holes is actually what happens when they collide. Again, at really extreme situations, right? So now you have these really weird objects where gravity makes space cease to exist and they collide. What happens? And they actually, if you stay with the trampoline analogy, now maybe instead of sitting, stand up, right? And have your friends, hold your friends in your arms and start dancing around, right? So you see that the trampoline, the surface of the trampoline starts to wobble and to create waves. And you can think of that as an analogy of what we call gravitational waves. So we have our black holes wobbling through the space-time and actually creating these ripples of our fabric. That the analogy is a trampoline, but it's really the fabric of space that is now giving up waves.
Yes.
And that's something that we have measured for the first time directly about 10 years ago now with a Laser Interferometer Gravitational Wave Observatory, or LIGO for short. And that was such an important discovery that actually got the Nobel Prize in Physics only 2 years later. So it really has changed our way of understanding the universe.
Yeah, that's so mind-boggling to think about, like, two things where space-time kind of ends and the interactions and what happens between, like, that's just so, it's so cool.
Yeah.
Before the detection of gravitational waves, how did people study black holes?
There were some observations, but not directly. So if you have a black hole and you have a star close by that, and they go around each other, if the star is close, it actually gets disrupted, and the black hole pulls matter off the star. And that is again a process that has a very high energy, very high temperature. So much so that we can detect that. So this was indirect detection of black holes. The other one was actually to look at stars that move at the center of our Milky Way. And they were following certain orbits. And from these orbits, so we can observe them, and we can actually observe them observe them over like decades. So we can actually compute what the mass of the object is that makes them orbit, makes these stars orbit. So what we find is that this is an object that is 4 million times as massive as our sun, but on a really small time scale. Length scale. So in a really small region of space. And the best explanation that we have for that is a black hole. And that actually was part of the Nobel Prize in Physics in 2020 for Andrea Ghez and Reinhard Genzel and their teams, who have observed these stars and concluded that there must be a black hole at the center of our very own galaxy.
I see. This might be a very silly question, but you talk about two black holes and measuring like the gravitational waves from that. Is like a black hole in a star, just the star probably isn't massive enough to measure? Okay.
It depends a little bit how close they are. If they are very close, or if it's a very compact star that is very close, then yes, they also will produce these gravitational waves, these ripples in space-time. That we can then measure. And maybe to come back to your question, how did we know about black holes? The observations I just told you about, but also on the theoretical side, we were already developing these models of what happens if we have two black holes collide, or two very compact stars collide. So we already had a lot of this machinery, and actually that was necessary to make the first detection. It's one of the things that we are also doing in my group, where we do computer simulations of colliding black holes, and we compute the gravitational waves that are produced in this collision. And we need the theoretical model that we get from the computer simulation to compare to the data that we get from observations to match up what's going on there.
Yeah, Helvi gave us a great analogy for this earlier. So when you like have heard a song on the radio and you can't remember the name of it, but you kind of have the tune stuck in your head, there's like, I know Google does something like this. There are other apps like Shazam where you kind of hum a little bit of the tune into the computer, and it has this huge bank of songs, and so it can kind of match your funky little tune that you just sung to all these known songs. And that's analogous to what you're doing when you're creating this massive bank of gravitational waveforms.
Right. Yes.
So then when you observe something with a little more noise, you can identify the system that it came from.
That's right.
Yeah.
Yes. Yeah. And if you want to hear the song of the universe, if you have two black holes that are dancing around each other and merging, that might sound something like whoop. Another song might be if you have two of these very compact stars, and that might go more something like if a lot of drama happens afterwards.
Yes.
Yeah. Or you might have two black holes that are actually also spinning around each other. So think about your dancing, and you're actually also spinning around your own axis while you're doing this.
Mm-hmm.
And for black holes, that might sound something like woo 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 whoop. So all these songs of the universe, we need to create this template, this bank of templates of what the songs could sound like. And we call that a template bank. Sorry, it's a technical term, but it's a collection of all these possible songs that could be out there. Mm-hmm. And then we compare to what we actually measure, which is a analogous of me trying to actually sing, and that might sound something more like because I'm not very good at singing. Right? So now you try to match in this very noisy song that you get from the universe with your theoretical prediction, with a bank of songs that you created to find what matches up, because that tells you of what the origin of your wave was. Was it two black holes? Was it something that was rotating around each other? Or was it a star?
I love the little songs. Could you go through the songs and explain to me what's happening at each of those noises? That's incredible.
Okay. Maybe let's start with the first one, where you said we have two black holes. Maybe they have a similar mass, right? They are not doing much fancy stuff, not spinning. So they're just dancing around each other. And if you do this with your friend, and maybe you want to hold your arms and you spin around each other. So if you do that, it might be just a single frequency because you're orbiting at the same rate. This would be something like... But now what gravity does is actually bringing those two objects closer together. So if you are dancing with your friend, also try to get closer together. And when you do that, you see that you get faster and faster as you complete your orbit, which means if we think about a frequency, which indicates how fast this is changing, that your frequency becomes higher. Mm-hmm. So you get a higher pitched tone until they merge. So hence the whoop. So this is the increase in frequency, and the chirp at the end is when they merge. Wow. And it's actually called a chirp. It's very similar to bird song.
Is there any frequency that it cuts off at, or
it does cut off at a certain frequency, and that depends very much on how massive your black holes are. Okay. So if you have two objects that are very massive, the frequency is lower. So this is why for the black holes I did a whoop. So this is in the range of 100 hertz. If you take the signal that we measure with our gravitational wave detectors and you make this into sound, it might sound very much like what I just did. If you have two stars that are much lighter, so these compact stars that I mentioned before are called neutron stars, and they're putting all the mass that we have in our sun in a radius of about 10 kilometers, which is probably somewhere around 6 miles or so. So it's something that's very compact, but the mass of the sun. So this is at a much higher frequency, much higher pitch. So hence the two stars would be. If there's something, something going on afterwards, and not just a black hole, you get also a lot of drama afterwards. So this is where the songs come from.
Yeah. Fantastic. So you may be getting to this, but could you tell us a little bit about what happens when you have all your friends on the trampoline and the fabric is about to rip open? What's going on inside the black hole when that happens?
We actually don't know. So that's the honest answer. We would love to know, but we don't. So everything that we can observe is what happens outside the black hole. Inside, we have no clue, and we cannot actually get any information from there. So in the beginning, when you introduced, you're looking at black holes, and this is where, if you have light, not even light can escape. So think of light as something that can send you information. Right? So if light cannot escape from the black hole, how do you get information out? At the moment, we don't have anything classically that tells us what's going on inside.
Okay.
And if I think about theory, which is a lot of what I'm doing, we have Einstein's general relativity, which is our standard model of gravity that so far describes everything that we observe. But it also predicts this really ending of space that we mentioned before. In physics terms, we call that a singularity. And to me, that's an indication that that's probably where Einstein's theory breaks down and needs to be replaced by something more fundamental. That's a better description. Just like I did the analogy in the beginning, where we know Newtonian gravity from everyday life, but it has to be replaced by Einstein's gravity to explain phenomena with very high gravity, with very high velocities. So now we are again at a place where our theory, Einstein's theory, now seems to break down, and it needs to be replaced by something more fundamental that we don't really know what it is. So we call it quantum gravity, where we want to combine gravity that we observe on astrophysical scales, or large scales, if you think about galaxies and the size of the universe, and things that can be described at the microscopic scale, very small scale, if you think about particles. And combining that is actually really an open question. In physics, we don't know how to do this. And when you were asking about why do I look at extremes, is that because I think looking at black holes might be a good place to start finding hints of what could go beyond Einstein. It's one of the things that we also do in my group at Illinois in the physics department.
Yeah, that's very exciting. What are there kind of ideas of what could be happening in the quantum gravity of these extreme situations?
So there are different ideas, different theories that could go anywhere from we have to make curvature even higher, have to modify how our equations look like. Maybe space itself has a very different structure, and we don't know. And to be honest, I'm not someone who builds these models. So I'm talking to my colleagues who do, and there are actually quite similar predictions on how Einstein's theory needs to be modified, how it needs to be extended. So what I do is to take those predictions and say, okay, if I take this, how does my black hole now look like? How is it different from, say, the standard black hole by Einstein, where I know everything if I know its mass and how it spins around itself? Now there may be additional information. And how does that affect our black hole collisions? Right? How does it affect the sound of the universe that we were discussing earlier? This is some of the things that I'm interested in and that we're working at in our group. And again, we now extend our database of songs so that we are able to compare any new predictions of going beyond Einstein with our observational data, with what we get from the universe.
That's really interesting. So you can test some of these modified theories of gravity.
That's what we want to do. Yeah.
Very cool.
Awesome. Could you talk a little bit about working with NCSA to develop the Einstein Toolkit?
The NCSA is the National Center for Supercomputing Applications, which is basically a really big computer at the University of Illinois.
That's right. Yes. I mentioned before that we do large computer simulations of colliding black holes. Now, to do these simulations, we need software. Right? We need a computer program to do that for us. And the Einstein Toolkit is a computer program that allows us to simulate or to compute these collisions of black holes, collisions of neutron stars. The Einstein Toolkit actually has a long history, and I would say even was born here in Urbana-Champaign at the National Center for Supercomputing Application about 20 years ago. And it's an open source software. That means it's public. Everyone can use it. Even you can go to our website, download it, and try to do your own black hole simulation. And everyone can contribute. So we have actually collaborators all over the world who might write a new piece of software that we then review and include. And we say, we want to test gravity and we need to go beyond Einstein. This is a new code, a module in our software, which is something that we have done. So, long story short, very roundabout answer to your question. We have been working with colleagues at the National Center for Supercomputing Applications, and in particular Dr. Roland Haas, to develop further the Einstein toolkit, so to make new additions. Now we are also working on making the software more efficient to run efficiently on in large computing centers, to use GPUs instead of CPUs, and hopefully make those simulations more efficient, because we need a large number of simulations to create all this database of songs. So this is where it comes back to, and it's been really fun to work on this and work with our colleagues.
How much computing power does it take to like create one of those songs?
Typically, we would run on about 200 CPUs for 1 week. Wow, give or take. It depends a little bit on what our actual system is, but yes, this is about how long it takes.
That's so cool.
Yeah.
That's very interesting. So another project that you're involved with, the Laser Interferometer Space Antenna, known as LISA, is a project proposed by NASA and the European Space Agency. It is an instrument orbiting Earth that can detect gravitational waves. What does LISA hope to detect that is not possible with current detectors?
Okay, good. So thanks for this question. This is really great. Let me backtrack a little bit, because I described the songs of the universe earlier, and I said, if I have two black holes that merge, probably give you a song at about 100 hertz. That is the case if your black holes are about 10 times, 15 times as massive as our sun. Now, I also mentioned the really what we call supermassive black hole at the center of galaxies. So we're talking 1 million times the mass of the sun. If two of these times the mass of the sun black holes collide, their waves will be in the millihertz frequency range, so 1,000 times lower frequency than the chirp that we heard before. In order to measure that, we need to go to space. So here on Earth, we have a lot of noise from, say, seismic interaction. So things like earthquake, or even just a truck going down the street can produce noise at about 10 hertz. So we cannot listen to lower frequencies. So we have to go to space. One part is the noise. The other thing is now we also need detectors that have a much longer length, and we're talking about a setup where we have 3 satellites in a triangle. We are shooting laser light from these satellites to each other, and we do that to time their arrival. And if the arrival time changes, that tells us something about the distance, the change in the distance between our satellites. So far, so good. We're talking about a distance of 2.5 million kilometers, and maybe you can help me put that into miles. It's probably somewhere around 2 miles.
200 million kilometers or 200 kilometers?
No, 2.5 million kilometers. So it's probably somewhere around 2 million miles apart from each other, give or take. And you want to measure this, a change in that distance as accurately as the size of a human hair, or less.
So that's about 1.5 million miles.
Okay, good. Sorry about the wrong conversion, but it's a huge distance, and we're trying to measure really, really small changes in that. And that tells us something about supermassive black holes colliding, like the one that we have in the center of our Milky Way. So think about, having 2 galaxies that might collide. Each of them has a supermassive black hole, maybe 1 million times the mass of the sun and 200 million times the mass of the sun colliding, and then generating these low frequency waves that we are looking for. Yeah. Or you could have a star or a small black hole orbiting, so dancing around a very massive black hole for a very long time. And this again would give us a signal in the millihertz regime that is very long, and we're trying to measure those.
Is there anything like particularly interesting that you think would happen at the millihertz regime in the millihertz regime?
Yeah, so these are new sources for us, right? What we measure here on Earth are black holes that have been born in the destros of massive stars.
Mm-hmm.
For these very massive black holes at the center of galaxies, we don't actually know for sure how they have formed in the first place, so that they could have grown into these million or even billion times the mass of the sun monsters that they are. So this is, one of the questions, or what I described, a small black hole orbiting around a big one for many, 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 many orbits is something that we wouldn't even be able to measure here on Earth. So it's a new type of source that allows us to listen to the universe. And it allows, LISA is so sensitive that it allows us to listen further back in time. So to larger distances means, because all the information is traveling at the speed of light, it means further away, means also further in the past. So that is, it makes it very, very exciting.
I see. So it's basically you're kind of building the timeline more if you're able to.
That's right. That's
okay.
right.
Wow.
That's right. Yeah, and the cool thing is gravitational waves are interacting very weakly with anything that's in between. So if you have an optical signal or a radio signal coming from somewhere, then it interacts with a matter that's between where it came from and Earth, and might be diluted or might even be absorbed, and you don't measure it in the first place. Gravitational waves don't have that interaction, so they come almost uninterrupted to us from very far in the past.
And with the enormous black holes in the millihertz range, do we not know much about them because we weren't able to go far enough back in the timeline to know anything about them, or?
I'm not sure that's necessarily the case. It's more a question of where do we start, right? So how do I grow a black hole that has a mass of, say, 6 million times the mass of the sun? You have to start somewhere, right? And you say, okay, if I now have a lot of other stars around it or a lot of matter that falls into the black hole. This is how a black hole grows. Okay, now you can think about how fast does this happen? How much does it take to reach a million times the mass of the sun? And then you can go backwards and say, oh, if I do that, then probably I have to start with something that already has 1,000 times the mass of the sun, give or take. And what these objects might be is still a question mark. So there are several ideas that I think I hope we will be able to test with these observations. Yeah.
Okay, thank you. Yeah. That's really fun.
That's very exciting. So when is the LISA detector expected to be sent into space and to be operational?
So that's expected for the 2030s. And actually very good news. In the beginning of last year, so January 2024, ESA and NASA approved the LISA mission. And now it's in the phase where they're looking for contractors to build these satellites and put it in space. And I think, so there are still a few options to choose, what goes into the satellite, what materials and so on. But I think this will be frozen relatively soon. And then it is going to be built. And that takes surprisingly long. So if you think about space missions, it's a long time scale. So we're thinking a decade in the future.
Yeah, still, that's very exciting. Yes. Could you talk a little bit about an additional research project, the collaboration you are developing with Illinois physics professor Smitha Vishwara?
Yes, I'm very happy to. That's kind of a toy project for both of us. And we talked about black holes, we talked a lot about gravitational waves, but we also talked about, strong fields and what can we learn, strong gravity. And the project with Smita is one of those where we are thinking about not astrophysics, but can there be analogies between astrophysics and gravity and condensed matter systems. So she is an expert on materials and condensed matter theory. So let me just give you an example of something that we've been toying with. So it's a really very early stages and we are just exploring. But there is a mechanism called superradiance. What does it mean? It's essentially an enhancement mechanism, something where you have put radiation in and you get more radiation out. Well, that sounds very much like a laser.
Can you clarify how that doesn't violate like a mass conservation? Like you put radiation in and you get more out?
So in the end it works out that it actually doesn't violate any conservation laws, but there are things like excitations, excited states.
Okay.
But so there was a main idea. So basically we are coming from this, the laser, the basis for a laser is that you have this kind of enhancement of radiation, right? In black holes, there's something somewhat similar where you throw a wave at a black hole, and if the black hole is spinning around its own axis, then this wave can actually extract some of the energy of the black hole and come out with more energy at the end. And this is what's called super radiance, so enhanced radiation. And so we started thinking about, whether there could be analogies in these very different systems. Right, one is a black hole, one is a laser. Could there be a black hole laser? So we're exploring some of these analogies also to see, can we learn from each other? Are there phenomena in black holes or in gravitation that might be interesting to look for in these material systems, and vice versa? Is there something that people in materials have seen that we might want to look for in black hole phenomenology? So this is something very exploratory, very risky and challenging, but I think also very exciting.
Yeah, that is very exciting. Have there been collaborations between material science and astrophysicists in the past?
I'm sure they have, and but I think for me personally, this is something new. Yes.
Yeah, that's very exciting.
I'm very curious about under what conditions you get this enhanced radiation out of the black hole.
So you have that if the wave that you throw at it has a very, very low frequency.
Okay.
Yeah. And I'm wondering whether it might be easier to think about this with particles.
Okay.
Which is a process actually sort of by Penrose. When you take a particle that is going to undergo nuclear fission, so decay, and you time it such that your particle decays very close to the black hole, just outside the horizon. There's a special region if you have a rotating black hole, and if you time it right, then your particle decays in the special region. Some of it goes in, some of it comes out. And if you then think about this mass or energy balances, actually turns out that the particle that, so because you're losing energy as a particle falls in, the one that comes out has to have more energy. And what I was describing is essentially this, but for waves.
Oh. So you mentioned you were inspired by Hawking's A Brief History of Time. When you studied at Cambridge, you met him. What were your experiences with meeting him like?
Very interesting. And so yes, first of all, I was fortunate enough to actually meet him when I was a postdoctoral researcher in Cambridge. He would actually come into the office almost every day unless he was traveling. And in Cambridge, we had a coffee hour every morning at 11 where scientists would just gather and chat with each other and talk about different ideas. And sometimes he would also come there. And in terms of interactions, it was very difficult because he, of course, couldn't really speak, right? So he had the computer and would either prepare questions, or if you were trying to discuss, you would try to answer short answers. And my mentor during the postdoc was actually a former PhD student of Stephen, so he would be able to help translate. So this was kind of the office experience. And I also remember one of the evenings, so I had my office just at the exit. And I was working late until 7, and he was leaving and actually said in his computerized voice, "Good evening." And I was so shocked that I didn't, for a moment, I thought, okay, well, what's going on? And by the time I actually reacted, he was already on the way out. But that was, it was very fun. And I also, I think just before I left Cambridge, I by chance got invited to one of his private parties for Guy Fawkes Night on the 5th of November. And I think what had happened is that someone wanted to have a photograph with him and interaction with him, and would in turn sponsor fireworks. Stephen loved fireworks, so he had a fireworks party in early November and had invited some of the members from the department, and I was fortunate enough to meet him there, and it was very interesting.
Yeah, that's exciting. That must have been so meaningful because that was a really formative part of your interest in astrophysics, and to get to actually spend time and interact with that person.
That's right.
I imagine it would be very surreal at the beginning, but just exciting overall.
Yeah, exactly. And I mean, once you were there, we are all colleagues. So even though he was, of course, this famous physicist, there he was a colleague.
Yeah, that's incredibly validating.
Yeah,
imagine.
Yeah.
To be seeing that person as a peer.
Yeah, to go from like reading the books, reading, kind of being inspired by them, to being like, oh yeah, this is my colleague. That's
I mean, of course, I was still in awe, but I think the way people acted around each other was like, yes, we are all scientists here.
Yeah.
This, was a really interesting, really great experience.
Yeah, fantastic. So you started as a faculty member at Illinois during COVID. Can you we also started as graduate students during COVID. We came in 2020.
We'll share that in common.
So we all have that in common. Can you kind of talk a little bit about that experience, kind of starting during that time?
Yeah, so I think in the beginning was daunting. So I should say I arrived here in January 2020, so just before the pandemic hit, right? And I was lucky enough to already meet some of my new colleagues here in the first 2.5 months before everything shut down. And I think that was very helpful to form first connections.
Yeah, definitely.
And I have to admit, the first, or the rest of that first semester, so spring 2020, from March until May, I was actually just trying to really work and survive, in the sense that I was assigned to one of our big undergraduate classes, where we have about 1,000 students. I did these big classes with engineering and physics and science students. After that semester, this is when I was actually taking a breath and tried to see how to navigate the personal life. And I have to say that here our colleagues have been extremely warm and extremely welcoming. And reached out, even people that I didn't know, like Nadia Mason or Vidya Marwan, who said, you're new, how are you doing? How are you holding up? Are you doing okay? And that, I think, for me was very important. And it to me also shows that in the department, it's not just a bunch of scientists. We're also almost like a family looking out to each other. So that's something that for me is what University of Illinois also is. And having colleagues and admin support these really stressful times to try and make it work for everyone. And I'm saying that because I've been, talking to colleagues elsewhere, actually across the globe, where they had very different experiences. And so I'm really grateful for the team that we had here and that we have here to go through this and what was a very trying time.
Yeah, I completely agree. And it really just, all it takes is like a small check-in to make such a big difference in making someone feel safe. So talking a little bit about interests outside of physics, so you recently featured in some local theater productions. In Rajiv Joseph's Describe the Night, you played Virginia. The Atlantic Theater described the play as, quote, set in Russia over the course of 90 years. This thrilling and epic new play traces the stories of 7 men and women connected by history, myth, and conspiracy theories, end quote. What motivated you to audition, and what was your experience starring in this role despite being relatively new to theater?
Okay. To answer your first question, I actually should maybe share a little bit about the background of what the play is about, and maybe my own background as well.
Yeah.
So the play, Describe the Night, takes us on a journey from 1920s Poland and the Russian-Polish War to 1940s purges in the Soviet Union to 1989, Eastern Germany, just before and just after the fall of the Berlin Wall, and then 2010, when the plane with the Polish government on board had a severe accident, actually going to commemorate the 1920s war site that featured in the play.
Oh, okay.
So this is a connection. The play itself, the scenes are in non-chronological order. So we would start in 1920 and then jump to 2010 and then go back to 1940s and then to 1980s. So my character was the wife of the chief of the security services in the 1940s Soviet Union, surviving that, and then in the 1980s, late 1980s, my character was an old grandmother with her granddaughter being observed by, at the time, a KGB agent who is now the president of Russia. So this is what we're talking about.
Oh, okay.
So it's that is a story, but it also takes us on a question and a journey of what is true and what is fiction, right? Or one of the more or less quotes is, if we are sitting here, we're looking at the night sky, and each of us would describe the night sky. Which of those descriptions is more true? And
what a perfect connection for you. It's a different epistemology of looking at the night sky, a different way of knowing.
Yeah. But it's also really exploring what is true, what is false. In an age of, fake news, what is fake and what is real, and what is said to be real and true. And the reason why I auditioned in the first place is actually my very personal history. I was born, as you said in the beginning, in Eastern Germany. I was a 6-year-old kid when the Berlin Wall came down, and so I have some memories. I think a lot of it is family memories on what it is to live in an authoritarian regime where there was no freedom of movement. There was a Berlin Wall, meaning from where I grew up, 100 kilometers, so 70 miles west, we were not allowed to go. And you had to be very careful of what you're saying. So for me, freedom of speech, freedom of movement is something that's, personally, this is my own opinion, something that's very important to me. Yeah. And when I heard about this play and read parts of it, it really resonated with me. I said, this is something that touches upon my personal history, but it's also extremely important, thinking the times that we are living in. So I'm really glad that we put this on at the Station Theatre last year in May, directed by Latrell Bright, who is a fantastic person, and she's a professor in theatre studies who has put this on. And an overall experience, we had an international team of actors, of people who helped us behind the scenes and develop this play with very different and diverse backgrounds. And I think that really made a huge difference. And we also were a mix of seasoned actors and newcomers like myself. So it was a great experience, a lot of fun doing it, but I think also a lot of reflection on what this actually means in different contexts.
Yeah. What a great way to kind of explore those questions, maybe even like process some of your own experiences through that art form. And especially when in theater, you're physically embodying that person. You're not just creating some external art. You're literally stepping into the role. I imagine it's a very powerful way to experience and kind of confront some of those questions. And that's something I also love about the Station Theater is they make beautiful productions, but anybody can audition and anyone can be a part. And so that's really cool to see.
It's cool to hear that they have a good mix of like experience levels. And from what I heard about it, you were also one of the main one of the main roles as well.
Yeah. For me, it actually was a surprise. So I went to the auditions and said, "Oh, let's see what comes out of it." I didn't expect to actually, be on stage, and it was a lot of fun, and I'm really grateful for this opportunity.
Yeah. Wait, did you feel like nervous because this was your first theater experience?
In the auditions, yes. As we developed the play, because we really grew together as a family, so we were really there for each other also on stage. So I think I was less nervous than I would have expected.
Yes, I feel like performing with a group is really, really helpful, especially if it's people that you feel close to and you feel really safe with. It can make it a much more fun experience.
Yes.
Do you plan to do any like theater in the future?
Maybe, yeah. So I think if there's things that are interesting that are coming up, I will definitely audition.
Yeah.
And if the time permits, yes.
Yes. Of course. Yeah, great. So I think this brings us to our final question. So we like to end each episode with the same question. In physics, emergence is used to describe a behavior which occurs at large scales but not at small scales. In other words, for an emergent system, the whole is greater than the sum of its parts. For example, when blackbirds flock together, the group will move and bend in a way that the individual bird does not. Can you give us an example of emergence from your work or experience?
Yeah, so that's the one that I had to really think
we can brainstorm together.
Yeah. No, because there's nothing that I can see immediately in my work. So let me, if it's okay, just go a little bit in a roundabout, because I went to a really fantastic workshop last summer, where they brought together experts in fluid dynamics. So essentially the physics of fluids, of how would water move, or if you have disks and jets that can form around black holes. So they had experts on that. They brought people in like myself who are experts in gravity and high energy theory, and in fluid dynamics. So what I said, the study of fluids. There, I think people have thought much more about what's called emergent phenomena. So what do I mean by that? You could think about describing your fluid, your water, really at the smallest scale, where you look at what are my molecules doing, how are they moving, how do I describe them? And there are different ways on how you might describe this. Right? And it's actually not always clear what is a right description for this microscopic movement. But then if you zoom out, if you go to actually describe how the water as a whole flows, you have this kind of emergence of a similar way of describing this. Okay, so why do I go in a roundabout way? Because I was thinking in gravity, we don't really have that. And then I was thinking, wait a second. We've been thinking about these extensions of Einstein's theory of gravity, where we are trying to connect gravity with the quantum world. Right, so I told you before, quantum gravity is one of these huge question marks that we have in our understanding of the universe. And there are different ideas out there. So think of that as an analogy of describing the almost microscopic structure of the universe. We have different ideas of how this could look like. But then as you go to larger scales, you have this emergent behavior that's now described by Einstein. So this is kind of the closest that I can come up with, and I mean, this is more an idea that came up when we were discussing this in this workshop. It's not something that I can really support with a mathematical calculation. So this is very speculative in that sense. But I thought this might be good connection to emergence.
Yeah. And so you're sort of in an analogous way to how you're working with Smitha to sort of draw parallels between condensed matter and astrophysics at this fluid dynamics workshop. You're trying to draw parallels between like fluid mechanics and gravity. Okay. Yes. That's very exciting. That's very cool. That was a great answer. Thank you so much.
That was fantastic.
So sadly, I think that's all we have time for today. I personally would love to ask you questions about black holes for like a long time. Forever. And theater and how they all fit together. But that's all we have time for today. Thank you so much for coming on. Helvi, it's great to have you. And to our listeners, thanks for listening and stay connected.
For further readings and resources about the topics covered in today's episode, check out the links in the description. Thanks for listening and stay connected.